the second lecture. So I'll just remind you, where we stopped last time. So I wrote down the generalized heat ensemble for the total lattice, which is this formula here. And I remind you also this is the Ln. And that, the Lax matrix is the Jacobi matrix, it's diagonal, tri-diagonal. And the quantity which we would like to know in the context of generalized hydrodynamics, if there's a key role, is the density of states. Okay. Now, when I first looked at this problem, I thought, oh, it must be somewhere in the book. But the point is that, even if I put IID, which is some general IID random variable here in this Jacobi matrix, I mean, there will be, maybe statements like, you have a smooth density of states, something like this. But actually writing down an explicit formula, it's simply not known. All right. So that's one small difficulty. But then you look sort of in the literature, and of course, there are other integrable models, and particularly there's a famous result of Young and Young in 1969. So this is the Liebig model, like the delta Bose gas. And they actually write down, okay, so first you might think that the Liebig and the delta Bose gas is of a totally different formula. That's not really the case. I mean, and, of course, it's a very different model, and then you do the beta ansatz to solve it. But this formula actually stays more or less intact, except for the fact that you have also something of this type, but the eigenvalues which appear here are not computed in terms of a Lax matrix, but they do come from what are called the beta root equations, right? I mean, so it's a nonlinear function, so to speak. And then also the a priori measure is sort of somewhat different. I mean, here I have some continuous in the case of the Liebig model. I mean, it's just sort of just counting. I mean, you just have integers. But nevertheless, I mean, they actually write down a free energy function as a function of the density of states, and the minimizer of that this free energy function is actually the density of the states in the case of the Liebig model, right? I mean, so you might wonder whether a similar structure actually appears also here. And sometimes you're lucky, and in this case, I mean, there is a work of Dumitrio and Edelman from 2002. Edelman, maybe I should write the full name. And what they were asking is actually, you start from a GUE random matrix, which is, fully occupied matrix, and you wonder whether you could transform it to a tri-diagonal matrix preserving the spectrum. And the answer was positive, and they realized, they first did it for the GUE, and they realized that I mean, okay, so they first for GUE, which is sort of beta equal to 2, but then they realized that, the beta sort of enters into a simple way in their formulas, and therefore it can be extended to arbitrary beta. Now I'm using this formula to do the reverse, so to speak. You see, I have a tri-diagonal matrix. I want to sort of use this theorem of Dumitrio and Edelman in order to sort of get an analysis, and then this is something which can be done. And okay, so let's see. This is not okay. So this can be done, but there's a sort of I mean, so there's a formula. I mean, for arbitrary n, I mean, there's a formula for the joint distribution of the eigenvalues. But with a small twist in the sense that, if I take literally this formula, I mean, I wouldn't know how to compute the distribution of the eigenvalues. But if you sort of make here, Okay, so maybe I should first make a plot what I want to do. I mean, so I have here my J, and then I have maybe 1 up to n. And this is the pressure. Now, if you want to do the Dimitri-Edelman, you have to replace this pressure by a linear ramp, right? I mean, so this is being replaced. So you have the constant pressure. Now I want to do sort of a linear ramp. I mean, so I put here simply some coefficient kappa times J, right? I mean, so that's this linear ramp. I mean, this is here, so to speak, the pressure, which becomes now dependent on the lattice size. Now, if I will immediately do a specific choice for this kappa, but what I state is sort of true for general kappa. Okay, and then what you find for the distribution, joint distribution of the eigenvalues is some sort of very very familiar formula. Well, then you find e to the minus. Well, I mean, because I'm doing the eigenvalues. I mean, this one, of course, is a simple term. That's just the sum from 1 up to n of the eigenvalues, and just as a function of this confining potential of the v. And then the other term is here simply the kappa, and here you find the familiar log gas. So this is log, maybe it's a factor of 2 here. Well, okay, of lambda j minus lambda I. Okay. And now you see what I want to do. I mean, this kappa is literally sort of arbitrary, but I mean, it's somehow clear. Eventually, what I would like to do is I would like to make. I do have this slope, but I want to have a small slope so that locally it will look like the density of states of the total lattice, right? I mean, and so in order to do this, I put the kappa equal to 2p over n, and then I have here. And so times 3. Okay, and so you see that once I allow for this modification, which is not so drastic, then I have something which sort of is pretty obvious. I mean, it's the log gas with a mean field interaction, right? So in the literature, this is called sort of the high temperature log gas, which sort of, I mean, to me always a little bit misleading because I regard this really as this is the usual. I would regard this as sort of not high temperature, but just sub-temperature because the energy and entropy are sort of well, I mean it's sort of both terms are actually extensive, right? And so when you do this, I mean, then of course you will get competition between energy and entropy, and you will get a free energy function, which I'm going to write down in a second, which contains both terms. When you do random matrix theory, I mean, they're sort of implicit in some sense, in a different situation where everything is sort of dominated by the energy and the entropy goes away. Anyway, so it's just terminology. But you can look at this. I mean, it's a mean field problem. There are lots of studies of mean field problems of this type, and so I'm just going to write down what is a free energy functional, and we'll sort of this can be done very with a lot of I mean, there's a lot of literature on which you can rely in order to do this. Okay, so okay, so maybe here I mean, this explains sort of the terminology why I call this confining potential. I mean, this V is sort of confining the eigenvalues. And well, it's also related to Dyson-Brownian motion. And anyway, so there are a lot of things which one could say. But let me just write down what is the free energy functional. Well, I mean, it's the obvious one. I'm going to say integral over W of W. Okay, so you have the confining potential. Then you have the entropy, which is the log of W. And then I put here -2. Let's see, why do I have here the minus sign? I didn't put the minus sign before. Just have a look. Okay, okay. Anyway, so okay, well, let me just first write it out. I mean, minus 2 integral over W prime, and then I have this logarithmic kernel. Okay, so and then I have to close this big bracket. Yeah. And now you would think that I mean, now you would think that if I do the minimizer of this problem, I mean, this will give me the density of states. So let me first sort of maybe I first have to explain what the variation problem is. I mean, I absorbed somehow, you know, this pressure term into this quadratic term, and so this has to be varied under the constraint. So the rho W, of course, is because it's the density of states is positive. But it's not normalized to 1. I mean, it's normalized to P, right? I mean, this sort of, it's a convenient way to do it. And well, then you would say, you know, my density of states, I mean, that's the one which I actually really want to compute. It's nothing else but the minimizer. So which I call rho star. And, you know, when you look at Dyson-Brown in motion, these kind of things, I mean, you can verify that there's a unique minimizer. And okay, then you say, okay, that's fine. I mean, you know, just like in the Lieb-Lindiger model, I found sort of a variational problem, and that's my minimizer. That's not correct, actually. You see what I'm missing here when I write down this minimizer. You know, I ignored the fact that actually, you know, there's this linear ramping. So you know, the quantity which the rho star actually is. So so when I look at 1 over P rho star, so this is now normalized to 1. You see, I have to, you know, I mean, this is sort of slowly varying. So in each little segment, I will have my GGE of the total lattice. But the P parameter is still varying, and so the quantity which I get is the integral from 0 up to 1. So here I put the du for this variation. I mean, that just sort of goes from 0 to 1, and then then I will have you know, this is now the total density of states. So this is what I call rho Q. And then, of course, it will depend on these parameters U, P. And let me put it also for completeness, I mean, this confining potential. So this is the linear varying pressure which appears here, right? And then you see that if I switch it to the other side, I mean, the final result is that the rho Q. It's nothing else but the dp of the minimizer of this variation problem. Okay? And so I will come back to this. You see, this means that I mean, usually when you have such a free energy function, you would say this is sort of, you know, it gives you also not only, you know, information about the minimizer, it gives you also information about the large deviations of the density of states. But since there's sort of this funny ramping, I mean, you cannot do this argument. And I will show maybe, you know, in half an hour, so I will show you, you know, another free energy functional, which is also, you know, which also determines the large deviations. Okay, but anyway, so this is sort of the result, and now of course, you know, the fact that we have such a variation problem allows you to do, you know, many computations, you know, despite the fact that you never really know exactly, you know, I mean, to determine actually the minimizer explicitly can be done only in very special cases, I mean, like thermal equilibrium or so. In general, you know, but, you know, the fact that it's a solution of a minimizer, you know, you have sort of the Euler-Lagrange equations. And so let me just sort of write down what these Euler-Lagrange equations are. I'm not really using it, but you know, I just want to write it down once so that you can see that you know, you can do lots of computations and get sort of results on the solutions. I mean, so in that, you know, in this community, I mean, they are always called TBA equations. So this is not to be announced, but it's a thermodynamic beta ansatz. And so, I call them also TBA equations. So let me write down what the TBA is. So you start from a quasi energy. These names are a little bit, when you think about a toda, maybe you don't have directly a physical picture, but it's still useful to use this kind of terminology. And for this, you write down. This is sort of somehow this comes from this comes sort of from the entropy term. I mean, so anyway, so you write the quasi energy as a function. What did I do? As a function of W. Is equal to this confining potential. And then there is a chemical potential mu, which is sort of the dual of P. Okay. And then we have, of course, this logarithmic term, which is minus the integral of dw prime. And okay, so now I put here phi toda. I come to a second. I put it like this, and then it's e to the minus f. Okay, so let me do this, in a moment, and then let me first sort of continue with writing down these TBA equations. Okay, so this is a nonlinear equation for the quasi energies. The parameters of my GGE are sitting over here. Well, I put here the dual of P. I mean, that's mu. And in fact, what turns out is that once you do it in this parameter, you will not have a unique solution. I mean, in fact, there's a twofold general solution. Let's say two solutions. I mean, this was numerically initial problem until people understood that, it's sort of a fairly trivial thing. I mean, you have something like this, and then if you go to the mu, you have something like this, and you get two solutions, right? But anyway, this is what's the case. And then once you have this, I mean, you sort of write down what people call the number density, which is then rho n, which is e to the minus the quasi energies, and then you write another quantity, which is the particle density, which happens to be the derivative with respect to mu of mu n. And then finally, you find that the density of states, so this is really the quantity which you want to have, is in this context nothing else but mu times rho p. Okay. Anyway, this is sort of this thermodynamic identities which are important, and of course here sort of functional identities, but when you look at this, you don't really see the structure immediately, but anyway, I mean, it's just sort of for completeness, I wanted to give this. So there was one thing which I wanted to, okay, so one thing I wanted to emphasize, you see, when you look at this, of course, what I call here phi toda, I mean, this is of course nothing else but 2 log of W minus W prime. And at least in this context, it's sort of a little bit surprising that, the kernel which appears here is very tightly connected to a scattering problem. You see, I showed you last time when you sort of do, well, I mean, just take 2 toda particles and let them scatter. Then you will find. Well, I wrote down for you what is this. Let's last lecture I wrote down for you what the scattering shift of the toda lattice is. It's just exactly this logarithm, right? And so this is a somewhat strange feature of these integrable systems, that the dynamical quantity appears directly sort of, as a key entry in either, when you look at this sort of free energy function or when you look at the TBA equation. I mean, quantum mechanically, it's not so surprising because, somehow the eigenvalues determine both the dynamics and the statics directly, right? But here okay, so that's the case. All right, so this is all what I wanted to say about the DOS. I mean, maybe there are some questions. Good moment to ask. So, yeah.
Can you summarize again the study that you're doing? Because I'm a bit lost in it.
No, what was that?
I mean, what's the connection between these two?
Between this one and this one?
This.
Well, I mean, well, no, I mean, I mean, it's just the words which I'm using from sort of what is usually used in generalized hydrodynamics and in sort of quantum mechanical integrable models, right? But these are all quantities which sort of are simply, think of them just as definitions. But this one is actually, I mean, the equation which I wrote down is actually the Euler-Lagrange equation for that free energy function, right? I mean, you don't see this immediately, but there are sort of some intermediate steps. I mean, would be pointless to do this at the blackboard, right? But it's really the very naive thing, right? I mean, you just take this. I mean, it has a unique minimizer. You linearize around the minimizer, and then you see what kind of equation you get. Just the usual Euler-Lagrange equation. There's nothing deep behind it. But I mean, the fact that it looks exactly like this. I mean, okay, you just have to believe me at that moment, right? I mean. And so, if you want to do numerics, I mean, I mean, one way to do it is actually to start directly from this equation and try to solve this numerically, right? It's actually not a very good idea for the total lattice, because the total lattice, has in the background has the Dyson-Brown motion. It's actually much more efficient to simulate the Dyson-Brown motion. Dyson-Brown motion, where you give the minimizer rho star, and then numerically differentiate that quantity, right? I mean, so. It yields the same result, right? But it's sort of a different mathematical tool to do it. Okay. I mean, this is of course very specific for the total. I mean, the fact that you compute, let's say, the density of states or the analog of the density of states, via the TBA. I mean, that's sort of a completely standard procedure, right? I mean, okay, so it's
quite straightforward to solve that equation.
What was that?
It's quite straightforward to solve that equation.
Yeah, that's right. Yeah. It's not very difficult. No, but you see what happened. Okay, anyway. What happened? I mean, since these things, what happened is that people started wanted to see the dependence on mu, and then at some point they realized that. Because you have this non-uniqueness. I mean, that they are sort of, the numerical code simply, became divergent, right? I mean, that's when you sort of, see the non-uniqueness, right? And then of course okay. All right. So now let me come to the main part here. So I erase this a little bit, and I want to come to this is now 2.5. 2.4, yeah. So now I want to compute the currents, right? Okay. Okay, so well, the average currents. I mean, GGE average currents. Okay. And maybe I should write down what the currents are. And so you just take one of the conserved quantities, Qj. This is lattice J. I mean, that's the index n. And then, of course, it's a discrete conservation law. So, I call this curly J n at the lattice J. And then, of course, it's a difference. Now, I should emphasize that, the current, already the densities are not unique, really. You see, I mean, you have different ways of splitting it up. I mean, the total conserved quantity is, of course, unique. But when you sort of define the densities, there's some arbitrariness. And it's the same for the currents. I mean, there's some arbitrariness, but, on the hydrodynamic scale, I mean, you sort of fix some convention, and the large scale behavior would not be sort of changed at all. But here I'm sort of using the convention which when I differentiate, this sort of is determined by the choice of the QJs. Okay, so I have done that, and now there's of course still my Q silver. I mean, I have so this is the free volume, and this we computed already is minus PJ plus PJ plus 1. Okay, and so you make this somewhat trivial observation that which mentioned already, that the density of the free volume its current is also conserved, and that's a feature which you also have in other models. So in particular, when you look at spin models, it works in the following way. I mean, so then maybe I have a spin model, let's say the H, and then I do a sum over J, and here I have my energy density. And for spin models, what happens is that when you, I mean, that the energy, that's sort of the analog of the mass, so to speak, in these spin models. And so what actually happens is that, I mean, not in all models, but in quite a large range of models, when you look at the energy current, this is then something like what we had. I mean, maybe this index J over here, and here I put J plus 1. Okay. So it turns out that just like in this case, it's the energy current which is actually conserved. Right? I mean, so this is the energy current, but the energy current itself is a conserved quantity. So this, in all the XXC models and these kind of things, this is always what happens. There are models where this is not the case. Then the method which I'm going to explain simply doesn't work, and there's no substitution for that. But once you have sort of one conserved quantity, I mean, then so once you have a current which itself is conserved, I mean, you just need a single one. Then the method which I'm showing you here for the total lattice works also in this case. Anyway, so now let's first do the. We want to compute. Maybe we should write out more explicitly what this current is. So let me do this for a moment. Let me just see. Yeah. So okay. So before we want to do sort of the empirical density just of the eigenvalues, now we can write down a similar formula for the current. So let me just do this. So this is sort of what one would call the empirical current. And well, I mean, it's 1 over n. It's the summation j equal 1 up to n, and then of course you put here your delta function, and then of course I mean you just look at okay. Sorry, I mean was going too quick. I didn't tell you what this object actually is, right? So maybe I should have told you. Okay, so let me write this. So. Here, of course, things are sort of fairly explicit. I mean, so it's Ln, and then what I call L down and JJ. Now L is the usual Lax matrix, which is still sort of indicated over here, and L means that this one is the lower triangle. Well, yeah, it's well, okay, but yeah, I don't know. Yeah, okay, it's a lower triangle. Okay, I mean, so it's simply everything is 0, and then I just put here sort of days. I mean, this is what I mean, right? So it's a very simple expression, right? And now, of course, you can write it in terms of the eigenvalues, and then of course you see that expressions sort of become not so easy. I mean, you have the AI. I mean, these are, of course, the variables which you have anyhow. But now you actually also need the eigenfunctions. So sum over I, so it's a scalar product of I plus 1. Okay, and then I looked for quite some time at this expression and tried to sort of see what would be the limit somehow, under some GHD. I never could see this, right? I mean, it looks so, since once you somehow having information about this is sorry. I mean, this is it's sitting like this, right? I mean, it's the same vector here, right? It's the eigenvector corresponding to this eigenvalue and then this particular matrix elements. Okay, I couldn't see this, but then you know, there was some moment where I realized that there's a very simple solution where you don't really have to look at these eigenvalues at all, but you do some other identities which at first sight, don't seem to be so powerful, but at the end of the day, I mean, you get what you want. And so let me just sort of explain how to do this. Okay, so now I'm going to write down sort of a few standard quantities for the total lattice. I mean, so you could think of finite volume, but I always think here in terms of infinite volume, but I mean, where you do exactly the infinite volume limit, I mean, that's sort of a different story. So let me do just a static correlator. So this is something, it's a matrix and it depends on the two lattice sides. And what I do is I take Q, I just want to do this in the same way I do my M at I, and then I take the QJ, and I mean, it depends only on the difference. And then I truncate, this is connected, and then I have here the index for my GHD, right? I mean, it's just the whatever charge correlation or the sort of the density correlations with the two conserved densities. Okay, so this is what I call the static correlator. And then, of course, whenever you have this quantity depending on index, I mean, you can also define total quantity where I just simply leave out where I leave out the index. Well, sorry. So S7 and then it's a susceptibility. I sum over everything and I take here the M and from that definition, right? Okay, so that's a static susceptibility or total correlator. All right. So we have this quantity. Okay, then now the same thing I can do for the field current. So this is field because I have the Q here. I can do the field current object, which it's just exactly the same definition. I mean, I give it a different name. It's BMN. And okay, so maybe I should yeah, okay, so here I want to sort of do a simplification in my notation. I want to sort of put this as QM, and then I put a semicolon QN, and then I put the PV, right? I mean, so this means that just exactly what I said. I mean, I take first the space-dependent correlator like this, and then I do the sum over here. Okay, it's just a definition of this operation. Okay, so for the current, of course, I will do the same thing. I mean, so the only thing what I change is that instead of this argument, I put the corresponding current. So this is the JM, and then I put here the QN. Okay, so up to this moment, I was just definition. So I should put the semicolon. I mean, this is what I mean, right? I mean, so you do the local and then you do the sum. Okay, and now what is sort of known, and then it seems to be sort of, totally general. I mean, it's quantum mechanical, stochastic, whatever you do, because it just relies on the conservation law. I mean, so the fact that you have a conservation law implies that this matrix, despite the fact that it looks highly asymmetric, is actually a symmetric matrix. Again, it's one of these simple identities which, of course, you can produce at the blackboard, but then okay, it's not a deep result. It just really relies on the conservation law. All right, so now comes sort of the twist. I mean, so now let's try to compute the average current. I mean, so I want to do the average current 0. Okay, and well, I put my indices. I mean, it's always sort of the GHD average. Okay. Well, okay, there I am. And then now how would I produce one of these matrices? Well, I mean, that's sort of quite clear. I could simply do the derivative with respect to P. if I do the derivative with respect to p, then from the exponential of the generalized Gibbs ensemble, I will get the Q0. Right? All right, so let's do this. I mean, so there's a minus sign because of the exponential is a minus sign, and then you see that what I get is simply this quantity here, and then well, I have to put the semicolon because it's extended, and then I differentiate sort of with an extended, very extensive quantity. But anyway, so I get the semicolon, and so here I have the m. No, sorry, I get the 0 down, right? Okay, so this is minus b n 0. Now this is equal to minus b 0 n. I mean, that's the symmetry. Okay. Now, what is the minus b 0 n? I mean, well, that's just well, I mean, you see the b0 is now the b0 is the current of the zero field, but the current of the zero field, I have erased, well, okay, I erased it. I mean, it was already on the board, but the cover of the zeroth field is nothing but the Q1. You see, I mean, this is this is a stretch, and the corresponding current is simply the momentum. I mean, so here I will see the Q0. No, Q1, sorry. It's a current of the zero of the zeroth field, the current of the stretch. That's Q1, and then I get here the Qn. Okay. And so now we found a somewhat unexpected connection, namely if I try to compute this particular derivative of the current, then it's connected to the susceptibility. So this means it's connected to the fluctuations of the density of states. Now, but this is something which I know how to do. We had this free energy functional, and I just have to do Gaussian fluctuation theory for this free energy functional, and then I get actually an expression for this quantity. All right, so let me do this. So again, there are lots of formulas in between which I'm leaving out, but the basic principle is quite clear. Right, I mean, you have this free energy functional, which has some minimum, and then we have a Gaussian fluctuation theory, which solves the quadratic approximation, and okay, so I just want to show one small identity. I mean, because otherwise it's maybe too quick. Okay, so you see, I mean, if I want to do this. If I want to do these fluctuations, I mean, it's always it's fluctuations relative to this object which was defined with the linear ramping, right? I mean, so if I do, so let me call C stars, or I mean, whatever. What is the name for that sign? Okay, anyway, so anyway, it's just sort of it's an operator which gives you the covariance, right? And so I want to maybe write it, between two test functions, I mean, whatever, theta 1 or theta n. I mean, these are polynomials in my particular case, right? So this is the quantity which appears here, right? And so this would be the operator which defines the covariance. I mean, this is basically the covariance of my Gaussian fluctuation field, and then the two components which I use. I mean, so this is in this notation. I mean, it's just a function. It's just a function w, and this is the function w to the power n. And the only point what I want to get to is, it's the same thing what I argued already for the density of states. I mean, this is actually related to the QQ correlation again, by doing this integral from 0 to 1 du, and then you have to put here the Q1. You see, this is the quantity which I can compute. I mean, That's a Q1, and then I have to put here the Qn. And this is not at the GGE at the parameter UP times V, right? So these are really my total objects. These are the ones which I get from doing the fluctuation theory for the formula which for the log gas. Okay. All right, and now you see that when you do the same thing as before, I mean you see that if then you get that the dp of my current is equal to the dp of this quantity up here, right? I mean, you just sort of shift it over. I mean, you substitute, and then you get here p times the theta 1, and then I get this matrix or this operator, and then that's the theta n. Okay, and so you see that when you look at this formula, you get for free an extra derivative in p. Right? Now, once you have this extra derivative of p, this means that the difference, has to be constant. And now you evaluate these quantities, let's say at very low density, where you know how these things behave. I mean, so you know that the constant which appears is actually 0, and the final result which you get from this is that the average current is given by this particular formula. I mean, so it's the pressure, then I have theta 1. I mean, that's simply, I mean, okay, I'm looking at this side. I mean, this is just sort of the inner product in L2, and they have one test function which is W, the other one is W to the power n, and here's an operator which I never told you what it really looks like, right? And then I consider theta n. Okay. All right, so it's a little bit gymnastics, but nothing really very deep what's happened. But at the end of the day, I get sort of a formula for the average current. I mean, it's something which I wanted to have. And on the right hand side, I get something, which I can, this operator I know because I can analyze sufficiently well the fluctuation theory for the log gas. Okay, so that's fine. Okay, so now comes again the gymnastics, which again I'm not going to show, but it's based on what I raised over here. It's based on these identities which I get from the TBA equations. Okay, now of course you do this gymnastics if you want to. How should I say? I mean, because there are prior results. I mean, I sort of roughly know what the gymnastics should actually give, right? I mean, so it's not the sort of there's already some goal. Anyway, the result of the gymnastics is that I can write this current. So this is the analog of the density of states, but now for the currents, right? I mean, so if I take the moments of this quantity, I will get just, are determined by this particular, just by the expectation of the nth current. I mean, so this is PV. Okay, so this density of states, I mean, I can write in a different way. I mean, I can write it as OP. I mean, that's something which I had introduced already. And then there's something which people call the effective velocity. And then there's something which comes from the lattice. I mean, then maybe I should not really go too deeply into it. I mean, this when you do the fluid, I mean, this term actually disappears. Okay, and PV. And then this is something which I call Q1, right? All right, so that's fine. I mean, since I haven't told you what the effective velocity is, I mean, it's just sort of some sort of rewriting, right? I mean, so here I have the moment of this quantity, and now here I'm looking directly at the quantity itself, right? And then I can write it in this particular way. And then, of course, the effective velocity is something which we have seen already in Amol's talk, or maybe also in other talks. I've certainly Benjamin was writing this, would imagine at least. Well, I mean, so it's the V plus, and now you get again, you know, this logarithmic kernel, I mean, which I now write as the scattering shift of the total lattice. So this is V minus W, and then you get this linear equation. Okay. And of course, you know, the worst with which go with this equation is I mean, you have your space time, and so here's x, and then here's t. So here's some GHD, which is, you know, which has the parameters p and v. I mean, so, you know, and sort of imagine this, and then you know, you sort of mark one phasor particle which is sort of sitting over here, and then, you know, which has sort of like a bare velocity, which is this v. But, you know, in actual fact, it's sort of doing a little bit more complicated, sort of kind of effective, sort of moving according to effective velocity. And this is sort of then, this effective velocity is then given by this formula. Okay. Okay, so now the 2 points to say. This formula, of course, is extremely beautiful. You know, okay, so in my first lecture, I emphasized, you know, the date 2016. It was in 2016 where people sort of realized that there was this formula, okay? I mean, you correct me, I mean, if it sort of get it wrong, but I think that that's sort of what was sort of, in some sense, now, once you see this formula, you know, you say, hooray, I mean, you know, the scattering shift is something which I sort of know from my model, and therefore I can immediately write down what the effective velocity is, and I will do this in a moment. I can immediately write down what my hydrodynamic equations are. I can sort of bypass all kind of, you know, complicated construction, which maybe you have to do in order to get to this. I mean, I can sort of, I sort of know immediately what I have to do, right? And then it's fairly, once I have the TBA, and then this equation is a fairly simple recipe, okay? Now here, you know, it comes to, you know, I'm sort of juggling with these matrices. But when I first saw this equation, and, you know, people, you know, tell me, you know, the intuition, I mean, okay, you say that, you know, you have here this razor, and then it sort of, you know, hits from the right and from the left, and then it sort of makes this jump. I mean, you know, was a very nice argument, but then it looked to me like an absolutely drastic assumption, because, you know, you're sort of putting for rate equation into a highly correlated system. And, you know, when you look at low density, of course, I'm immediately willing to believe that kind of argument. But when you look at very high density, where things are sort of packed together, then, you know, the validity of this formula sort of didn't look at that stage. I mean, totally, you know, not so obvious to me, I must say, right? But here, this argument, you see, it just goes through. I mean, there's no limitation on whatever, right? I mean, it's just a simple identity. Yeah? And it works for all models whenever you have sort of this particular structure of the currents. Okay, so let's see. This is, yeah, so now let me write down what is the generalized hydrodynamics. And of course, there's not so much of a surprise. I mean, let me use the fluid version here. Because, you know, for the lattice, I mean, you have this extra term, you know, where the equation sort of looks a little bit less familiar. I mean, the extra term comes from the lattice because, you know, just if you do, I mean, if you just do free particles on the lattice, I mean, then, you know, they sort of go, you know, they stick at the lattice side, so to speak, and therefore, you know, you have this term. Anyway, it's not a very deep point. I mean, so the hydrodynamic equation are then actually written for this particle function. So I mean the integral over rho p. I mean, u rho p is equal to 1, right? I mean, so this is the free volume, and so you know, this function sort of has all the information about the eigenvalues and about the free volume. So this function sort of, if you want, so you know, it's a local density of states plus the free volume. And now this becomes now, of course, a function of x and t, but also of w. W is sort of the spectral parameter. This is the label for the conserved quantities. And then, this has a rather simple expression. I mean, you just take the V effective, of course, at the same argument. I put here a semicolon. I mean, this is space-time, and this is of the spectral parameter. And then I have to multiply this with the rho p, xt. And this is equal to 0. So you get a very simple hydrodynamic equation. And now, of course, you can use this equation to do all kinds of things, which I don't want to go into. And okay, so that just fits very nicely. So I want to sort of, well, unless there are specific questions on that part, I want to discuss two things a little bit. So I want to come back to these large deviations, right? And I want to come back to what I claim the similarity to the Lieb-Liniger model. Okay, so let me see what I wanted to say here. Yeah, I wanted to come back. That's right. Okay, so now let me this is 2.6 now, I guess. Now, that's not completely clear what to do. And, when I use this scheme, I simply don't know what to do, right? I mean, I would not know how to get, the formulas. But there's another beautiful strategy is that, now I'm thinking in the fluid picture. I mean, so I'm thinking of particles on the line. And now you do, what is not so unusual. I mean, you want to put your GHD and you want to put it into a confining potential, right? And what is the confining potential you can choose? I mean, it's the exponential potential, right? I mean, so here I take a decaying exponential for the first particle. It's of Q1, and here I put the increasing for Qn, right? I mean, so this is supposed to be. Yeah. All right. But you see, the particles are not confined. I mean, this goes to infinity, but the particle can also go to infinity, right? I mean, so they're not strictly confined. I mean, but of course, for thermodynamic purposes, you would say that they have a particular volume. But if I put n particles and if I put this sort of, of order n, I mean, that's of the usual thermodynamic limit which you would do. Okay. Now, the main point of this exercise is that. In the first lecture, I introduced the asymptotic velocities, which are the lambda J, and I introduced the scattering shift. I guess I called it phi something plus minus or plus minus phi anyway, something like that. Okay, of the J's particle. Now these happen to be the canonical transformation from the P and Q's to the eigenvalues and to the scattering shifts. These are so-called scattering coordinates. You see, it's on the torus you have action and angle variables, but if I look on the line, I mean, then you have scattering coordinates, but it's also a canonical transformation. And so, of course, the idea would be, I'm not writing down any formulas, but the idea is you just write down your usual GHD and then, try to transform this expression in terms of scattering coordinates. That has a big advantage that, I have this trace of VL. I mean, this is nothing else but the sum over V of lambda J. So this term trivializes under this transformation. But the volume measure is, of course, a total mess. I mean, I just don't know what to do. But it so happens that for the total lattice, you know, there are very explicit expressions for this transformation. And so what you realize is that under this transformation, this particular, only this very particular, it must have exactly the right sort of, you know, parameter, decay parameter of the exponential. You can actually write down simple formulas for the scattering shift as a function of the P and Qs. Okay, it's so simple that you can actually do the integral explicitly over the scattering shifts. And so at the end of the day, for this kind of boundary conditions, you can write down again a closed formula for the distribution of the eigenvalues. Unfortunately, it looks a little bit more complicated than you know the log gas. Yeah. Anyway, so if I do all these kind of things, then I can write down. It would take a little bit more time to really explain what I do. I just want to write down one formula. Namely, you find then you find okay. So now I want to do in these coordinates. I want to do the free energy function now. And this looks now of the following type. I mean, so first of all, you again, I mean, you know, you vary over densities and whatever, you know, these densities are normalized to 1 in this case, okay? And then you introduce something which is called the space density. And it's a similar sort of idea. I mean, you know, you have a space density which is sort of, you know, it's a free volume. And so this was new in my notation, but I mean, so this is average free volume. But now, you know, these particles, since they are shifted, I mean, they need a little bit more space. And so you get a new space density, which is called OS. So OS, of course, is a function, right? I mean, okay, so this is just a number, right? And then, so this is the free volume of my GHD. And then you get plus, and then it's easier to write this as an operator. And of course, I mean, you know, the kernel of W prime is that what we have all the time, right? 2 log of W minus W prime. Anyway, so you define this particular object. It's a space of, okay. And then in terms of this, you find a very nice and simple formula. I mean, so my free energy function. Well, I mean, first of all, you get the free energy function from this one. I mean, this you can sort of think as a, you know, I'm using here L2 notation. I mean, so this would be just this confining potential of rho. I mean, this is the integral of the confining potential and the rho. So it's just this term over here. And then you have the relative entropy of, so S is now rho, that's a relative entropy relative to the space density of OS. And this is also the correct sort of free energy for the large deviations. And this is very, very, you know, I'm not writing this down, but it's very similar to the kind of identities you have for the delta Bose gas. Okay. So if I take the minimizer, that now I have to, if I take the minimizer, I really get the true density of states. Right? Okay, so there's one thing I wanted to say. Time is up. Well, okay, I think this is fine. I mean, I mean, okay. No, I still have 2 minutes. Okay. So let me just leave it like this. I mean, you can ask questions if you want to later on. And let me just sort of put sort of one which I just want to mention. Okay, so these are the narrative simulations. So, you know, there's Power is whatever. There's has a long name. I mean, so we have Kirchenbauer, Thomas Kirchenbauer. I mean, you have Masuko. Okay, anyways, so here there are also. I just want to sort of You can look it. You can look it up. I mean, so what? I mean, Ken McLaughlin is also one of the authors. Anyway, so you can look it up. I mean, what we did is we basically prepare, you know, the total in thermal equilibrium, right? And then in thermal equilibrium, we measure what are the dynamic correlators. I mean, so numerically, we look at something like Qn. J, let's say at HC correlated with UM at 0, in my well, okay, so this is thermal. And no, there's no huge. I've written it in sort of, you know, and I'm looking at the fluid variables. I mean, so we're looking at such kind of things. And well, N is sort of typically 0, 1, 2. I mean, we look at energy, momentum, and free volume, and so these correlation functions can be, you know, simulated with some effort, but with fairly high precision, and you could compare it to the linearized hydrodynamic equation, which, you know, I have erased over here. I mean, so you start linearizing about, let's say, thermal equilibrium. So this is, you would be linearizing around the density of states corresponding to thermal equilibrium, right? And then, you know, some formulas, of course, you have to do it numerically, and you really find, you know, absolutely, you have to look at the paper in order to be really impressed. I mean, you find really sort of, without any fitting, you find sort of a complete, you know, agreement between the numerical data and the linearized Euler equation. Okay, so thank you very much. I mean, next time we will focus on the probabilistic. I mean, so I'm not going to continue on the total.